Hello everyone, welcome to another episode of Math-321. So today we're going to continue Investigation 29, Group Isomorphisms and Invariants. Okay, these are the most important definitions from last time. So we talked about the concept informally of groups being essentially the same. So informal definition 29.3 was let G and H be finite groups. The group G is said to be essentially the same as H if the operation table for G can be transformed into the operation table for H by doing nothing more than renaming the elements of G and or reordering the rows and columns of G's operation table. So that was the informal concept, and then we built up to a formal definition. So definition 29.5, let G and H be groups. Notice they do not have to be finite. An isomorphism is a bijective function phi from G to H, such that for all xy in G, phi of x times y equals phi of x times phi of y. And then we discussed how that could actually look differently if one of the groups or both of the groups use addition rather than multiplication. If there is an isomorphism from the group G to the group H, we say that G is isomorphic to H, which is denoted with this symbol right down here. Okay, so let's go ahead and go over this. So let G be the set consisting of matrices of this form that's shown here, where X is a real number. And then notice that G is a subset of GL2R, that is the group of invertible 2x2 matrices with real entries under multiplication. Show that G is a subgroup of GL2R. Okay, so to show that it's a subgroup, we need to show that it is closed, it contains the identity from GL2R, and then it also contains the same inverses as in GL2R. Okay, so let's start with closed. Okay, so let's let, what should we call them? I don't know, A and B be elements of, maybe I'll call them G1 and G2. Let G1 and G2 be elements of, wow, that looks terrible, of G. Okay, then there exists some real numbers. Let's call them, oops, I used the existence symbol. I'm trying not to do that in this class. Then there exists some real numbers, let's call them X and Y in the reals, such that G1 is equal to a matrix where I'm going to put X in, and G2 is going to be equal to the same matrix but with Y. Okay, so then I just need to show that G1 times G2 is in G. So what is G1 times G2? So I'm going to multiply these two matrices. Hope you remember matrix multiplication, kind of important. Okay, so I'll do the first row times the first column. Let's see, that's going to be 1 times 1 and x times 0, so that's just 1. And then the first row in the second column, 1 times y and x times 1, so this is going to be x plus y. And then let's see, the second row in the first column is going to be 0, and then the last one will be 1. Okay, and this is in G, because x plus y will be a real number as well, if x and y are real numbers. Okay, so good, it is closed. And this is interesting too. What you're seeing here is that when x and y are your entries for your two elements, then the entry for their product is actually the sum of those. That's kind of interesting. Okay, so then for the identity is going to be in there because 0 is a real number. Okay, so let me just say it like this, 0 is a real number, so you know what the identity is in GL2R, it's this identity matrix, so that will be in G. And then finally for the inverses, so based on what we got for part 1, where we found that when we multiply two elements together, it basically just adds that top right entry. So that means we can see what the inverses should be pretty quickly. So let me do it like this. So let G be in, little g be in big G. Then there exists x in the real numbers such that little g equals 1x 0 1. Okay, then I'm going to say the following. Then negative x is also in the real numbers. So I'll call this something else, I don't know, h. So h equals 1 minus x 0 G1 is in G, and GH is going to equal, just like we showed on part 1, this is going to be x plus negative x right here, which is going to give us the identity matrix. So H is going to be G inverse, and that is in group G. Okay, so group G is indeed a subgroup of GL2R. Now part B was to say what familiar group you think this is isomorphic to, and you should focus on the fact that when you multiply two elements in this group, there's only basically one thing that's unique about them, and it's that upper right corner element. So let me just say that on this slide here. So the only thing that distinguishes elements in G is the upper right corner entry. And when you do two elements multiplied together like this, you get that it just adds together the two upper right corner entries like this. So this would suggest that all you're basically doing is addition of real numbers. So this would suggest G is isomorphic to the real numbers under addition. Okay, I hope you guys can see why that makes sense. All right, so now let's do another activity, and in this one we're actually going to prove what I said on the last slide, which is that this is isomorphic to, this group G is isomorphic to the real numbers under multiplication, or sorry, under addition. So go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go over part A. So let G be the same as that group in the last activity, and then let phi be a map from G to the real numbers defined by phi of one of those matrices in G is just equal to the upper right hand corner entry. So first we have to show that phi is injective. So we can just do this the same way for all injective proofs. So we're just going to let there be two elements in G. So I'll just say G1 and G2 are in G, and suppose that they have the same image under this map. So phi of G1 equals phi of G2. Okay, so we need to actually expand a little bit on what G1 and G2 are and make them into matrices. So since they're in this group G, there exist two real numbers for each of them to have in their right corner. I guess that's not plural, is it? Okay. In the reals, such that G1 equals this matrix, and then G2 equals this other matrix with Y. Okay, then since they have the same image under the map, so phi of G1 equals phi of G2, well, what is phi of G1 and phi of G2? Those are just x and y, aren't they? So that implies that x equals y. So then from there, we can actually say that the two matrices must have actually been the same, right? Because they had the same entries. Where's my eraser? Okay. And so that means that G1 and G2 were the same. Okay, and that's it. Okay, so for surjective, this is actually quite easy because of the way the function is defined. So we're going to let there be an element in the codomain. So let x be in the real numbers. So you start with an element in the codomain, and then you have to find that there's an element in the domain that maps to this element in the codomain. Maybe I should have called it y, I don't know. I usually use y here. Okay, so what would x be? So x would be, so the element that's going to map to this is going to be, I don't know that I want to call it x though, that's confusing because we're already using that. Let me do it like this. Then let G equal this, so 0, oops, not 0, 1, y, 0, and 1 will be an element of G. And if we plug this element into the function phi of G, that is going to equal phi of this matrix, and then that's just going to be y. Okay, so we showed that there's an element in the domain that maps to this element that we picked in the codomain. So that means it's surjective. Okay, and then finally show that phi preserves the operation of g, that is, show that for all x and y in the real numbers, that phi of two elements from G mapped together or multiplied together like that equals actually the sum of their images. So over here, this is the G operation, and then over on the right hand side, this is the real numbers operation. And you always, regardless of whether they're multiplication or whether they're addition, you always do the operation for G inside of the parentheses for phi on the left, and then on the right you do the operation for the other group outside of phi on the right. Okay, so that's why one of them is multiplication and one is addition. Okay, so anyway, we just have to show this. So phi, so the left-hand side is the following. So I'm going to just do the operation that is inside the parentheses there. So this is going to become 1 x plus y, 0 and 1, like we showed on the last problem. And so this is just going to be x plus y. Okay, and then the right-hand side is so what you're going to get from phi of the first matrix is x, and then from the second one you're going to get y. So the left-hand side equals the right-hand side. So that's it. Okay, so now that we've practiced a little bit with showing that something is isomorphic, let's talk a little bit more about some basic properties of isomorphism. So since an isomorphism from group G to group H preserves the structure of G, there are certain things we can expect all isomorphisms to do. So for example, you can expect that the isomorphism is going to map the identity of G to the identity of H. I think this is a typo here. So the next activity will show us actually some more properties that we can expect from isomorphisms. Okay, so here's activity 29.9. Go ahead and pause the video and try this activity, and then we'll go over it. Okay, let's go over it. So let phi be an isomorphism from a group G to a group H, and then let EG and EH be the identities of G and H respectively. Part A, prove that phi of EG equals EH. So the hint here is it suffices to show that H times phi of EG equals H for some H, little h in big H. And the reason why that suffices is because we still do have group cancellation, so we can cancel H on the left and the right of that equation and get that phi of EG equals EH. You may need to use the fact that phi is a surjection. Okay, so I'm going to use the property of isomorphism, which is the following. So since phi is an isomorphism, for all, let's call them G1 and G2 in G, we have that phi of G1 times G2 equals phi of G1 times phi of G2, like that. So let's see, which one should I do? I don't know, G2 equal EG, so I'm just going to plug that in for G2. Then phi of G1 times EG is going to equal phi of G1 times phi of EG. Okay, and then that implies we can simplify and get that phi of G1 equals phi of G1 times phi of EG. Okay, and then what I'm going to do is multiply on the left of each side by the inverse of phi of G1. I don't know what phi of G1 actually is, but it is some element of H, so I'm just going to multiply by its inverse. So I'm going to multiply by this, phi of G1, G1 inverse, to get the following. So this will be phi of G1 inverse times phi of G1, so that's going to cancel out. And then the same thing on the right. Or you could just use the group cancellation law, that's fine too. Inverse times phi of g1 times phi of EG. Okay, so then this yields... Okay, so what happens when you cancel out these two elements here? That actually is going to leave you not with EG, but with EH. Because now that you've plugged them into phi, they're now elements of group H. Okay, so this is EH and EH right there. So this means that EH equals EH times, oops, phi of, oops, wow, making a lot of mistakes, EG. Okay, and then from there, actually, you can just cancel out the EH on the right because you don't need to write EH times an element of H. It can just be by itself. So this is telling us that EH equals phi of EG, like that. Okay. Okay, so part B, prove that phi of A inverse equals the inverse of phi of A for all A and G. And then the hint here is to just show that it suffices to show that, or sorry, the hint is that it suffices to show that phi of A times phi of A inverse equals EH. Okay, so since we know that phi is an isomorphism, so I'm just writing the same thing I did on the last slide. So for all G1 and G2 in G, phi of G1, G2 equals phi of G1 times phi of G2. Okay, so we can plug in G1 is going to be A, and then G2 is going to be A inverse. Okay, so then we have that phi of, oops, not G1, it's going to be A times A inverse equals phi of A times phi of A inverse. And then what happens on the left is that is going to become just phi of E of G, okay, because A and A inverse are G elements. And then on the right, of course, we still have this. Okay, and then on the left, what's that going to become? That's why we had to do part A first. So that's going to be EH equals phi of A times phi of A inverse. And then that right there is enough to tell us that those two elements are inverses of each other, since when you multiply them, you get the identity. So phi of A and phi of A inverse are inverses in H. Okay. All right, part C, let A be an element of G. Prove that phi of A to the K equals phi of A all raised to the K for all positive integers K. Okay, so since we're doing this for all positive integers K, I think we should do it by induction. All right, so let's give that a try. So let P of K be the statement it's just going to be this equation. So phi of A to the K equals phi of A all to the K. So for the basis step, we need to show P of 1. Or yeah, P of 1, because we're doing positive integers. So that'll be phi of A to the 1 equals just phi of A also to the 1. This is obvious. It's just the same thing on both sides. Okay, then for the inductive step, so we're going to assume that P of K is true. That is, I guess I should have done let P of N be the statement. Oh, whatever. So assume, I don't know, maybe I'll go back and change it. It's a little weird to use the same letter to mean different things. Okay, so anyway, assume P of K is true. That is, phi of A to the K equals quantity phi of A to the K. Then we need to show that P of K plus 1 is true. That is that phi of A to the K plus 1 equals quantity phi of a to the k plus 1. Okay, so let's see. The left-hand side, let's start with that. So the left-hand side is phi of a to the k plus 1. So we can separate a to the k plus 1 into a to the k times a. Okay, and then using the fact that phi is an isomorphism, we're allowed to separate it like this. Okay, because that phi preserves multiplication like that. So then we already know we can substitute in from our inductive assumption. Sorry about the car noise. I do live right on a street corner. That's a C. Then we can substitute from the P of K assumption. To get that phi of a to the k, which times phi of a, which is what we already had, is, this is going to be quantity phi of a to the k, and then another phi of a. And then so if we just combine those together, that is, just using rules of exponents, that is the k plus 1 power right there. Okay, so that's how you can prove that. All right, so last part, let A be an element of G using parts B and C, or use parts B and C to prove that phi of a to the k is equal to phi of a quantity to the k for all negative integers k. And this will complete the proof of the following theorem, and the theorem there just says that that equation is true for all integers k. Okay, so I'm just going to say let k be a negative integer. I need to actually get a positive integer to work with in order to be able to apply part C. So I'm going to do the following. Then I'm just going to say that negative k is a positive integer. Okay, I hope you're going to be able to handle that if I treat negative k as a positive thing. That is a little weird, I know. Okay, but then we can say the following. So then phi of a to the k can be written like this. So this is phi of a to the negative k, like that, which is the same as phi of a to the negative 1, so a inverse to the negative k. And we are allowed to bring a positive integer outside. So I'll just make a note of that. We can bring a positive integer outside phi to get that this is equal to phi of a inverse to the negative k, like that. Okay, and then so that was part C. So then by part, I'll just put a little note there that by part C. And then by part B, we can also bring the inverse part, the negative 1 power of a, we can also bring that outside. Let me start with what I had before. So the inverse to the negative k equals, okay, and then we can do it like this. So this will be phi of a inverse, oh, I don't want to use brackets because we have a special meaning for that, to the negative k, like that. Okay, and then we can combine those two powers back together like this. So this will be phi of a just to the k. Okay, I hope that made sense to you. Okay, so previously in the class we had discussed the concept of well-defined functions, and it is really important when you're choosing a function to show that two groups are isomorphic, you need to be really careful to choose a function that is well-defined, and that's not always as easy as it might seem. So the following activity is going to show us how this can kind of go wrong in a way that seems very natural. Okay, so here is preview activity 29.10. Go ahead and pause the video and try this activity, and then we'll go over it. Okay, let's go over this. So let F map each element A mod 3 in Z mod 3 to the element A mod 6 in Z mod 6. So does F preserve the group operation in Z3? Explain. Okay, so what they're really asking is the following. In other words, if we take the image of the sum of two elements like this, is that the same as the sum of the images of the two elements separately, like this? Oops. So is that the case? So that's what we need to check. So let's go ahead and check this. So let's let A and B be elements of Z3. So A mod 3 and B mod 3. Okay, then what is the image of their sum? And we're doing sums here, not products, because the operation in Z3 is sums, or addition. Okay, so how do you add two elements in Z3? You can just put them together inside of the brackets like that. Okay, and then according to how this function is defined, that is just going to be A plus B mod 6. Okay, and then on the other hand, on the other side, rather, of the equation, we get f of A mod 3 plus f of B mod 3 is going to be A mod 6 plus B mod 6. And then we can also do that addition inside of the brackets like that. So yes, the group operation is preserved according to this. So we get the same thing on both sides of that equation. So it doesn't matter whether we add first and then do the function, or whether we do the function first and then add after that. Okay, so let's look at part B here. Consider the following proof that f is an injection. Let A mod 3 and B mod 3 be elements of Z mod 3, and assume that f of A mod 3 equals f of B mod 3. Then A mod 6 would equal B mod 6, and so 6 would divide B minus A. Remember, that's what it means for two elements to be congruent mod 6. It means 6 divides their difference. So 6 divides B minus A. And then since 6 divides B minus A, 3 also divides B minus A, which implies that A mod 3 equals B mod 3. So that appears to be a proof that f is an injection. And that would imply that Z3 is isomorphic to the set f of Z3, so that's the image of all the elements of Z3 under the f mapping. So an image of a set like that will automatically be, how am I trying to say this? Like the domain Z3 is automatically going to be surjective onto its range. Okay, you don't have to check that if it's f of Z3. That's just the images of all of Z3. So f will be surjective onto the range like that. I'm not making any sense, sorry. What do you think about this conclusion? Explain your answer in detail. Okay, so this is really problematic, right? Because it's not right that it can be isomorphic to this set, and now I'm going to show you why. So Z3 can't be isomorphic to f of Z3 for the following reasons. For example, if we do 1 mod 6 plus 2 mod 6, that is equal to 3 mod 6, which is not the same as 0 mod 6. But when you do those two elements in Z3, 1 mod 3 plus 2 mod 3, you get 3 mod 3, which is 0 mod 3, right? So when you add 1 and 2 in Z3, you're supposed to get the identity, but when you add 1 and 2 in Z6, you don't get the identity. So it doesn't make sense for these two to be isomorphic. So f is not preserving the group structure. And so the real problem that's going on behind the scenes here is that this function is not well defined. And I mean the following by that. The function is not well defined because, for example, in Z3, the following two things are the same. 2, for example, mod 3 is the same as 5 mod 3. But f of 2 would be 2 mod 6, whereas f of 5 mod 3 would be 5 as well, according to the way we've defined the function. But we can't have the same element mapped to two different elements. That doesn't make sense. That's not even a function at that point. Okay, so f is not well defined, and that's why this part B is so weird. Okay, so I just want to say a little bit more about that. So preview activity 29.10 showed us that even if a function preserves the group operation and is a bijection, as that function in the last one was, it still won't be an isomorphism unless it is a well-defined function. So in other words, the function cannot map two different representations of the same element to two different elements, which is exactly what we saw on the last slide. So in general, when we say function, we do mean a well-defined function. And here, just to show you again, I think we had looked at this before, but here's the definition of a well-defined function. So let S and T be sets. A mapping f from S to T is well-defined if f of A equals f of B whenever A equals B in S. So if A and B are the same element, then they need to have the same output from the function. And here's a little activity for you to try. Just look at this mapping here, f from Q to Z, and tell me whether this is well-defined and why. Go ahead and pause the video and try that, then I'll go over it. Okay, so assuming you've already tried this, the answer is definitely no. So for example, here are two elements that are the same, but they have a different output. So for example, 4 over 2 is the same as 8 over 4, because those are both 2. But we would get f of 4 over 2 would be 6, and f of 8 over 4 would be 12. So that's no good. Okay, so now let's talk about the concept of disproving that groups are isomorphic. So the basic technique of proving an isomorphism between groups is always the same. You define a function, and then you show that the function is a bijection and that it preserves the group operation. Now, on the other hand, proving that two groups are not isomorphic requires a completely different approach. We can't just define a function and then show that it's either not a bijection or it doesn't preserve the group operation, because there's just so many possible functions between the two groups, and you would have to try every single function and show that it doesn't work. There may be a few cases where you can try this approach by sort of defining a general function where you never quite say what the formula is, but most of the time this is not going to work at all. So we need a different approach, and that will be provided by the next concept. Okay, so invariants. So a property that any property that isomorphic groups must share is known as an invariant. So invariants are properties that are preserved by isomorphism. So for example, if P is an invariant and a group G has property P, then any group to which G is isomorphic would also have to have property P. So these are properties like, being abelian, being cyclic, having 10 elements, those kind of properties. And if two groups do not both have an established invariant, then that means they cannot be isomorphic. So this is the general approach for proving that groups are not isomorphic, is to find some invariant that one has and the other does not have. Now keep in mind here, very important, invariants can be used to prove that two groups are not isomorphic, but they cannot be used to prove that two groups are isomorphic. So it's completely different approaches for proving that things are isomorphic as to proving that they're not isomorphic. You cannot use invariants to prove isomorphism. Okay, so here's a partial list of some invariants of group isomorphism, and there are more than these, but these are some ones that we know about already. So there's the number of elements. Two groups got to have the same elements, number of elements. Commutativity, so this could mean a lot of different things. It could mean being abelian. So if group G is isomorphic to group H and group G is abelian, then H also has to be abelian. But it could refer to other commutative properties. For example, like the size of the center of the groups would have to be the same, or even if if you look at what are they called, like the commutator groups where it's like everything that commutes with a certain element. Those would all have to match up as well. Then there's being cyclic, and then there's number of elements of each order, number of subgroups of each order. You could also put number of normal subgroups of each order. That would also work. And then being simple, which means having no normal subgroups that are not the whole group or the identity subgroup. Okay, so they didn't actually put an activity, sadly, in the book for you to prove that two groups are not isomorphic using one of these, so I just would like you guys to go ahead and try this activity that I inserted here, activity 29.13 and a half. Go ahead and pause the video and give this a try, and then we'll go over it. Okay, so let's go ahead and go over this. Show that Z4 and the external direct product of Z2 and Z2 cannot be isomorphic because Z4 is cyclic, but this external direct product of Z2 and Z2, that is not cyclic. Okay, so remember that Z4, this is the following congruence classes. So there's 0, and then there's 1, and then there's 2, and then there's 3. So to show that this is cyclic, we have to find one that actually generates all the rest of them. And the operation here is addition, so we'd be generating by integer multiples. So I'm going to show you that 1 actually generates all of these. So this is simply the integer multiples of 1. Again, because the group operation is addition and not multiplication. Okay, so this is just going to be, first there's 1, and then 2 times 1, that's 2, and then 3 times 1, that's 3, and then 4 times 1 is actually 0, and then once you've gotten all of them, you can stop. Okay, so that is cyclic because it's generated by 1. Now, on the other hand, the external direct product of Z2 and Z2, it consists of the following elements. So there are still 4 of them, but they're these ordered pairs where one element comes from the first group and then the other element comes from the other group. So it's these 4 elements. And you can see that this is not cyclic if you just try all of them. So first of all, the subgroup generated by, I think they're supposed to be in brackets actually, since they're still elements of Z2, right? That's a hassle. Okay. Brackets, 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 brackets. Okay, so if I do the cyclic subgroup generated by the first element, which is the identity element, that's just going to be that element again. Oh my gosh, these brackets, they're killing me. Okay, so you don't get anything there. And then the cyclic subgroup generated by the other elements, we can just go through all 4 of them and check. So this is going to be this element, and then this one, and then if I do 2 times this, I'm going to get, so 2 times 1 is going to actually be 0 because we're in Z2 for that element, and then 2 times 0 is obviously still 0. So as soon as you get the identity, then you're done. So just those 2 elements. And then the same is true for, it's actually exactly the same for this one. It's also going to be just an order 2 element. So this is going to be 0, and then 1. And then if I do 2 times this, I get, of course, 0 again, and then 2 times 1 is 0 in Z2. Okay, and then finally the last one. Okay, so I start with that element. And then if I do 2 times that element, I'm just going to get 0, 0. So once you get the identity, then you're done listing them all. So none of those are generating the whole group. So that is not a cyclic group. Okay, and that's it. Okay, so now let's talk about the concept of isomorphism classes. So we have a theorem here, theorem 29.14, which says the relation of group isomorphism is an equivalence relation on the set of all groups. So I don't want to show you the whole proof because we're kind of running out of time at the end of the class here, but here's just a little sketch of what you would need to do for this proof. So you would need to prove these 3 properties here. These are the properties of an equivalence relation. All equivalence relations have to be reflexive, symmetric, and transitive. So for the reflexive one, any group G will be isomorphic to itself because the identity map is actually an isomorphism. The identity map that just maps every element to itself, that is a bijection, and it also preserves the group operation. And then isomorphism will be symmetric because if you have 2 groups G and H that have an excuse me, that have an isomorphism phi between them from G to H, then the inverse function phi inverse, which you know always exists for a bijection, that will also actually be an isomorphism. Again, it's just a sketch, so I haven't proved that, but that's what you would need to do. So then if you can show that, then H will be isomorphic to G, so that would show that the isomorphism relation is symmetric. And then finally, for the transitive property, if you have three groups, G, H, and K, with isomorphisms phi from G to H and theta from H to K, then you can compose those two functions to do theta of phi, and that'll go from G to K, and you can show that that's an isomorphism as well. Of course, it'll be a bijection. We learned previously that a bijection composed with a bijection is another bijection, and then you just have to prove that it preserves the group operation. So that's what you would do to prove this theorem here. Okay, so now that we've learned that isomorphism is an equivalence relation, that means that isomorphism partitions the set of all groups into just disjoint equivalence classes, which we call isomorphism classes. So in particular, the set of all groups isomorphic to G is called the isomorphism class of G. So in investigation 31, which I believe will be the last investigation we're going to get to in detail, we will completely classify all finite abelian groups. In other words, we will show what isomorphism classes they belong to. So the problem of classifying all finite groups is still not solved, but we do know a few things. So for example, I have here the following, which is a list of the number of isomorphism classes, and that's denoted capital N of little n, for each possible number of group elements, little n. So for example, over here we can see that there's only one basically one different group of size 1, and that's just like the identity. And then there's only one group of size 2 up to isomorphism. So what I mean is all the groups of size 2 are isomorphic to each other. Same with groups of size 3, they're all isomorphic to each other. So basically Z3 is a group of size 3, so all of the groups of size 3 are isomorphic to Z3. And then for size 4 here, so there's only two different isomorphism classes for size 4, so there's pretty much basically up to isomorphism only two different groups of size 4. And we actually saw both of them earlier because we just recently proved in that activity that Z4 and the external direct product of Z2 and Z2 are not isomorphic to each other, so those are the two isomorphism classes. And then you can go through and look at this. Some of them are kind of interesting, like look how many groups there are of size 64. That's actually crazy. But for some reason there's fewer groups of size 96 than there are of group 60 or of size 64. That's interesting. I don't know why that is. Maybe because 64 is a power of 2. That might have something to do with it. One thing you can definitely see here is that like all of the prime group sizes, there's only one for those numbers. Or like, well, that's not prime. I don't know, yeah, like 11, 13. So that's an interesting thing that we'll learn later on, that for each prime group size, there's only one isomorphism class. So basically, if you have a prime number of elements, you must be isomorphic to ZP, where P is that prime number. All right, well, I'll see you next time, guys. That's it for today. It's a little bit short. Next time, we will finish up investigation 29.